Hello and welcome back to Casual Physics. This is video number 6 in the series on guesstimation, which is all about how to solve impossible problems as I like to describe it. Now, why is this important? Why do you need to be able to do this? Head back to video number 1 for the answer to that and check out videos 2 to 4 if anything doesn't make sense in this video. Why? Because in those earlier videos we introduce some essential tools and techniques that we're using throughout this series. Today is the last video on the theme of food. Previously, we calculated how many pickles were eaten in London last year, we figured out how much land we'd need to grow our own food, and now we're turning our attention to the end of the life cycle of food and, indeed all products, waste. Now, despite recent advances in recycling, for the most part, our waste still goes to landfill, which is more or less just one big hole in the ground. And the question is, how big is that hole and do we need to worry about it? That's what we're going to look at today. As always, we start with what do we know? We probably have a good sense of how much rubbish we create ourselves in any given week. But what about other people? We can't possibly know about them, and that's what makes this an impossible problem. And so what can we do? We can use what we know about ourselves and scale that up to represent the whole population. But what does that actually look like? The total volume, the tote, is the space we need to store all the rubbish, and it's just our individual contribution multiplied by the population. That's all. Now, this simple approach works really well as an approximation because it's very likely that you and me are just average people, and so our rubbish production habits are also probably just average. We're not likely to be super wasteful, but we're also likely not to be zero waste kind of people either. Let's start by guesstimating our individual contribution, and then we'll come back to look at the population afterwards. And let's begin with a sensible time frame of 1 week. How much rubbish do you make every week? What's the volume of it? Now, perhaps you know the volume of your bin, or perhaps you know some other numbers that can help you. Pause the video and have a think. For me, I don't know my bin size and I'm too lazy to go and check today, so I'm going to use the geometric mean. I know the total volume of my bin has to be more than 1 litre, but certainly less than 1,000 litres, which is a cubic metre. And so we get the square root of 1 times 1,000, which is approximately 30 litres. And by the way, side note, I actually went to check and it turns out my bin is 28 litres, so this is really not bad guesstimation at all. If you don't have a good sense about volume, that's okay. Another way we can think about rubbish is in terms of the mass. How many kilograms of rubbish do you make in a given week? Again, pause the video, have a think. If you don't have a clue, don't worry. The geometric mean has always got your back so long as you can come up with a sensible minimum and maximum. I think it's definitely more than 1 kilogram and less than 10 kilograms. Why? Because I know what a 10 kilo weight feels like, and taking out the rubbish just doesn't feel like that for me. So I think I produce roughly 3 kilograms of rubbish per week. Okay, so we have 2 measurements of how much rubbish we produce, the volume and the mass. And we can use these together to create a sanity check from something that we call density. Density is given by the Greek letter rho, and it's a measure of how much mass we have for the volume we have, and it's calculated by dividing the mass by the volume. In our case, we've got 3 kilograms of mass and 30 litres for the volume. As always, it's best to put things in standard international units. Mass in kilograms is fine, but the SI unit for volume is actually cubic meters. There are 1,000 litres in a cubic metre, and so we have to divide our 30 by 1,000 to do the conversion. In scientific notation, that's the same as 30 times 10 to the power of minus 3. And now let's clean things up a bit. As usual, we collect our units at the end, and I've taken the liberty of adding a negative power to my cubic metre unit to indicate that it's kilograms divided by cubic metres, in other words, kilograms per cubic metre. Okay, 30 times 10 to the minus 3 is the same as 3 times 10 to the power of minus 2. We're multiplying and dividing by 3 so we can cancel them out. And you may recall from video number 3 that when we divide by negative powers, it's the same as dividing by a fraction. and that effectively undoes the negative power. And so we end up with 10 to the power of 2, which is simply 100 kilograms per cubic meter. Density is a really good number to calculate because we can compare it with other well-known densities, and that can give us a sanity check. So for example, air is 1, water is 1000, and lead is 10,000 kilograms per cubic meter. These are really good numbers to have in your mental wiki, because now we can compare our 100 kilogram per cubic meter density that we've calculated. It's denser than air, and that's good because rubbish doesn't float like a helium balloon, but it's less dense than water, and that's good because rubbish bags do typically float in water. So this gives us confidence that the numbers that we've guesstimated are good. These kind of sanity checks are super helpful because honestly, we sometimes mess up when we're calculating and we need a way to sound the alarm bell. And in addition, density is a super helpful number because it can give us a sense of how much the rubbish can be compressed before it goes to landfill, and that will have an impact on how big the landfill needs to be, and that's the thing we're interested in. Here's one way to think about it. Our rubbish is made up of many things. Some things like metal, glass are more dense than water. They sink in water. We also have things like paper, card, plastics, which are less dense than water. They float on water. And so one could make the argument that if you could squeeze out all the air from the rubbish bag, then we probably end up with a mass of stuff that on average has a density of about water. If we compare the density of water to our rubbish bag, it's a factor of 10 higher. Now, I think it's very unlikely that our rubbish crushers are so good that they can squish out all of the air, and so I'm going to use the geometric mean to guesstimate the compression factor. It's got to be more than 1, and I think it's less than 10, and so we end up with a compression factor of around 3. And so every week, my 30 litres of rubbish ends up as 10 litres of compressed rubbish in landfill. And there are, of course, around 50 weeks in a year, and so that's 500 litres per year, which is 0.5 cubic metres of rubbish per person per year going to landfill. And so V-ind is 0.5. And that's the hard part of our guesstimation problem for today. The population, that's the easy bit. Just go ahead and pick your home country. For me here in the UK, it's about 70 million people. And so with a bit of mathematical jiggery-pokery, we can see that every year the UK would need 40 million cubic metres of space to store all of its rubbish. But what does this mean? It sounds like a big number, but how does this translate into land area? That's something that we have a lot more familiarity with. Now, to convert between volume and land area, we need to know the shape of the landfill. Now we'll assume the landfill is a cuboid, and this means that the volume is just the area multiplied by the depth. If we have the volume and the depth, we can actually calculate the area by simply dividing both sides of the equation by depth and then tidying things up a little. Now for the numbers. We know the volume, that's what we've just calculated. It's 4 times 10 to the power of 7. But what about the depth? What would you use here? Pause the video and have a think. I would say that the depth is more than 1 meter and less than 100 meters, and that gives us a geometric mean of 10 and therefore an area of 4 million square meters. Which sounds like a lot, but as always, we need to get some perspective. Let's consider our area to be a square. Then 4 million square meters is a square that is 2000 by 2000. And if we now turn everything into kilometers, then we get a 2 kilometer by 2 kilometer square, which is just a 4 square kilometer area. What sounded like a big area initially is actually not that much bigger than the official city of London, which is where most of the banks are. But you might say, okay, Matt, but we need to store our waste for longer than a year. Well, that's fine. Let's take 100 years. We need 100 times the area, so that's 400 square kilometers, and that's a square that is 20 kilometers by 20 kilometers. Well, that's just a bit bigger than the whole of inner London, which is starting to sound like a lot. But Again, let's continue to create more perspective. Let's compare this with the land area of the whole of the UK, which is 250,000 square kilometres. 400 as a proportion of 250,000 is the same as 4 divided by 2,500. And we can make this fraction easier to interpret by making the bottom a power of 10. And we can do this by multiplying and dividing by 4, and that's going to give us 16 divided by 10,000. Let's go ahead and turn this fraction into a percentage by multiplying by 100 and then tidying things up, which results in 0.16%. And so after 100 years, only 0.16% of the UK's land will be full of rubbish. Another way of putting that is to say that if all our rubbish went to landfill and we recycle nothing, then after 100 years, we would still have 99.84% of the land to use for everything else, other things. And when we say it like that, it definitely doesn't sound like much of a big deal. And I remember the first time I did this calculation, I was like, I was not expecting that at all. It made me do a double take. It made me think about all the recycling I do and made me question, why do I even do it? And that impulse may be the reason why we went to landfill to begin with. It doesn't sound like a big deal, and it isn't when we're just thinking about land area. But recycling is more than just about the land we're using. For example, how much rubbish ends up in the ocean? How much energy do we save by recycling versus making stuff from scratch? And those are just 2 examples. I'm sure there are many more. There's always more ways to think about things, and we can, of course, use the tools of guesstimation to think about them. We're not quite ready to talk about energy yet, but you could have a go at guesstimating how much rubbish goes into the ocean. You could, for example, estimate how big the Pacific garbage patch is. You could do that. I'm going to briefly sketch out how you do that now and leave it to you to have a go at filling in the details later, because I think you're ready to have a go at doing this yourself, especially because this is mostly just an exercise in using the geometric mean. First, how many people contribute to the rubbish production? Obviously less than 100% and probably more than 10%. Next, how long has the rubbish patch been building up for? Certainly more than 10 years and probably less than 100 years. Now, what fraction of the rubbish ends up in the ocean? That one's a bit more tricky. I'd say it's got to be more than 1% because human processes are just never that good, and probably less than 10%. Otherwise, government authorities would surely have clamped down years ago. Finally, how deep does the rubbish actually go in the ocean? If it's floating, then it's definitely less than 1 meter and probably more than 1 centimeter. Have a go at that problem, and I love to see your guesstimations in the comments section, and hopefully they will spark some good discussion. Okay, what's next? Now that I've mentioned the Pacific garbage patch, I'm going to use that as a convenient segue to talk about oceans and specifically sea level. How high can it get? That's what we're going to look at next time. Thanks as always for your time and attention. Take care, and I'll see you soon.